Well, so welcome. I would like to give a warm WAPOR welcome to all of our members, all of our guests, all of our chapter members from around the world for this morning's webinar, this afternoon's webinar, this evening's webinar, depending on your time zone. So today we're really looking at something that bridges three important and interesting topics for all of us. And so the first is non-response. And of course, non-response error is something that we all worry about as response rates decline pretty much in all settings, I think. The second is something related more to design and responsive design, something that is really just a wonderful innovation that we've seen in survey research that maybe helps us minimize response error. And the third is, of course, machine learning, something that is somewhat new and very exciting. And so we're just delighted that we're joined today by two researchers and experts in these topics. We're going to discuss some of the relationships between machine learning and responsive design. And so I am just delighted to be joined by Christoph Kern, who is an assistant professor of data science and statistics at LMU Munich. And I'm delighted to be joined by Jack Collins, who is a PhD candidate and a data scientist at the University of Mannheim. And so we very much hope you'll enjoy this presentation. As always, please put your comments and questions in the chat, or even more so in the Q&A, and we will get to them. Don't feel that you have to stay until the end for the questions. If you put them in during, and if they're relevant, we can maybe find a break in the middle, or we'll hold some time at the end for more detailed questions. And now with this, I would just really like to give a great thank you and welcome to Christoph Kern and Jack Collins.
Well, thank you very much. Also welcome from my side. Very excited to be here. Going to start sharing my screen now. Perfect. Right, and very excited to be co-presenting here this webinar. We will be talking about generalizable non-response prediction and machine learning-based adaptive designs, and I will take over sort of the first broader introduction part, where we'll give you some context and background, and then Jack will be taking over for part 2 and 3, where we'll first talk about non-response prediction in panel survey settings using novel advances in machine learning, specifically time series machine learning techniques and neural networks. And then for the third part, we'll be looking at generalizing ML predictions across different panel designs and panel studies. This also will bring us to the topic of pre-training, which I think is a quite exciting idea. Broadly speaking, the idea is to train a model, a non-response model, with data from a survey that is different to the survey that you want to essentially use for deploying your model and for making predictions. Also, we'll briefly touch on model interpretation in this context, which is often an important topic. And then for the last part, I would like to try to bring all of those different things together to actually share some very recent results where we talk about bridging predictions and adaptive designs towards prediction-based adaptive designs. All right. I'm hearing that the sound is not optimal. Okay, I'm hoping it will be better throughout. I'm trying to monitor it. I can switch to a different connection if it will not be better. Okay, yeah, thank you. Good. Starting with the overall problem setup. So we are, I think, well aware that unit non-response and attrition in panel surveys is a big issue, as it has consequences for data quality, which eventually also then compromises the integrity of research funding, since we understand that we lose sort of valuable panelists, and data quality leads to issues downstream when it comes to research findings, substantive research. Also, there's a understanding that there is a great promise of using predictive models to predict each participant's non-response propensity upfront, using the wide range of data that we typically have available in panel survey contexts. Combining this then gives us the great opportunity to potentially predict who non-responds upfront, and then also intervene such that there is a possibility to keep those respondents that are initially being identified as having a high risk of dropping out. This, of course, needs two important ingredients, which is not only accurate predictions, but also effective interventions, which then jointly essentially are needed to successfully build a machine learning prediction-based adaptive design. So this will be our broader setup in this context. So we have, for the most part, some data available from a given panel survey that we can use to learn patterns of non-response. So we have classic sets of predictors here available, demographic information, non-response history, and potentially also sort of the count of previously invited waves for a given participant. And then for the most part here, our setting will be that we'll talk about predicting non-response in the next panel wave. Although also we can envision here different outcomes as well. Then
I'm very sorry. The audio quality is breaking out again. I wonder maybe if you block your video, if that will give us enough bandwidth. I'm not sure, but sometimes that can work.
Yes, I can try that. Thank you for reminding me. Also, what I can do is, as I mentioned, to switch to another connection, but let's see whether that already helps. Okay, so starting with this slide again. The setup is that for the most part, we will have training data available from a given panel survey. A set of common predictors include demographic information, non-response history, and other information from a given participant over the previous waves. And our objective is to model or predict non-response in the next panel wave. Now, in the middle here, we have a number of options available for actually training such a model. Classic approaches include logistic regression. There's, however, also clearly an interest in moving to tree-based approaches. And then also we'll talk about other training approaches and modeling techniques later on. Then the last part is using those models, or the best one, to predict non-response sort of ahead of time. Clearly want to firstly evaluate the predictive performance, and then the latest step would be to use the predictions to actually inform an adaptive design. This general process has been used and analyzed and evaluated by a number of previous papers. And it does seem to be the case that those ML approaches can successfully predict non-response with a high accuracy, We have some papers listed here on the right-hand side with some performance measures. However, there's some lack, we feel, in studies that systematically compare many different modeling approaches using the same set of predictive performance measures and potentially also using different panel studies. So we'll come back to this later on, where we conducted a systematic comparison that looks at combining ML predictions and utilizing them across different panel designs, actually. However, broadly speaking, it does seem to be the case that tree-based models do perform quite well in this task compared to other approaches, although there's also it has to be noted that more classic approaches, such as logistic regression, often only perform a little worse, but also have the advantage of being more interpretable. However, there are also many novel techniques that are being explored and proposed in the machine learning community. Essentially, novel ML techniques are being proposed almost every week, all with the promise of improving prediction performance for complex tasks. First, latest advances include various models that are based on neural network architectures. Those models, however, are often proposed in somewhat different contexts, so not proposed for non-response prediction, but maybe for image data, audio data, or text data tasks. So we want to, however, still in our research and in the next slides also explore those novel approaches. Also, there's a tendency to, or kind of a modern approach in the ML context that essentially uses multiple data sources to pre-train a model and then fine-tune this model later on for specific downstream tasks. And also in our work that we want to demonstrate later on, we're sort of a little bit inspired by this approach of pre-training a model on some data that might be different to the data that you use later on for deployment. Right. This being said, in the following, we want to essentially look at 3 extensions to this standard approach. The first extension is here, the one in the middle, where we say, okay, how can we maybe improve using novel ML approaches and use them for non-response prediction? That will be the first section after this intro. The second section will be on the left-hand side, looking at different data sources and understanding whether we can essentially use pre-trained ML models across different panel designs to predict non-response. And then lastly, of course, the focus will be then at the end on adaptive survey designs that are informed by ML predictions. Good. And with this, I am handing it over to Jack for the first part, where we'll focus on novel ML approaches for non-response prediction.
Thank you very much, Christoph. I am going to go ahead and share my screen now. Going to full screen that. Pardon me, is that coming through on full screen? There it is. And I'll also ask Mr. Harrison, is my audio coming through loud and clear?
It is coming through fine. Thank you.
Brilliant. Thank you very much. G'day there, everybody. My name is John Collins. You can call me Jack. I'm a PhD candidate at the University of Mannheim, working with Christoph on this project. And what I'll present now is in this particular area of trying to see if we can introduce more sophisticated models to the pursuit of propensity modeling. This is from a paper that's been published in JSSAM, and we'll be presenting a brief overview of the results. So this is about trying to find some models that could help us do propensity modeling a little bit better. And the key message that we want to get across is that the temporal dimension matters, that panel data is time series data, and that if you take into account not just the information that you're collecting, but how you account for changes over time, you can improve that modeling. You can improve your predictive power. So there are several ways of accounting for the temporal dimension in propensity modeling. Those of you who are familiar with logistic regression, you could say, for example, add in a term for each time step. You could, for example, with any of these typical machine learning models, you could say, for example, take a participant's average non-response rate over all time, or you could take their average non-response rate over the last 2 waves, 3 waves, 5 waves, 6 waves of your panel. And these are all acceptable means of accounting for time in your panel. And the essential idea as to why time would matter is, well, let's just say that somebody exhibits some behaviors that are associated with non-response, but they exhibited it in the distant past, 10 waves ago. And since then, their behavior has changed. What is their risk of non-response relative to somebody who had a different behavior pattern or has exhibited riskier behavior, but recently? Will that result in more non-response in the near future, or will that just go away without them non-responding? So these are generally called temporal dependencies in the data, the fact that the order of events and the timing of events matters. And we wanted to know whether a recurrent neural network might do well here. So a recurrent neural network, and I'm sorry, but we won't be going into the details of neural networks or recurrent neural networks, but the important thing to understand about a recurrent neural network is that you can input a time series of data of any length, and the neural network will work out for you these temporal dependencies, what matters in terms of events from the distant past versus the approximate past. And like to tree-based models, they are flexible in the sense that they will automatically work out interactions between features or predictors, as opposed to something like, say, a simple unpenalized logistic regression, which won't account for interactions between variables unless you explicitly build in interaction terms. So we want to see whether recurrent neural networks exploit the time series nature of data better than a previous approach. How are we going to evaluate that? Well, we've touched on this briefly, but just because it's going to come up again and again over the course of the rest of the course of this presentation. How do you measure whether a model is making good predictions or not? And we say that we are concerned with 2 things in particular. One of them is precision, which is also known as the false positive rate. So high precision means that you're not getting a lot of false positives. False positives would be if I predict that somebody is going to non-respond in the next wave, and therefore I must target them with some kind of intervention, something to try and get them to stay in the panel. But as it turns out, they would have stayed in the panel if I had done nothing, and therefore my effort in trying to induce them to stay, my intervention, my extra cash incentive, what have you, would have been wasted, could have been allocated to somebody else. But at the same time, we don't want too many false negatives. And a high recall rate means that you don't have many false negatives. A false negative would be, I predicted that somebody is totally fine, they're not going to drop out, but then in the next wave they did non-respond, and therefore our model essentially missed them. And that's not the intended function of a model that helps you detect people who are going to non-respond. And we like to use a single number called area under receiver operator curve, and we won't go into the details of how that's calculated, but it essentially summarizes these 2 concerns. And it's a number that goes between 0.5 for the worst possible classifier, the worst possible estimator of whether somebody's going to not respond or not, and 1.0, which is a perfect classifier. So we've been talking about these numbers. We threw a few of those on the screen earlier, but rather than sort of telling you that, giving you these various metrics, we're going to step through an example. And where this is related to recurrent neural networks, first thing we're going to do here is we're going to show you the let's call it the state of the art. Let's call it a good practice that has been arrived on in the literature before adoption of recurrent neural networks. Let's take a look at how that works, and then let's compare that to the recurrent neural networks. Okay, so stepping through an example of how we might predict non-response with this approach that's emerged from previous studies. So what you see here is we have taken a random forest model and we have trained it on all data from the GESIS panel. That is a German general population panel survey started in 2013. So we had about 6 years worth of data. They run waves 2 or 3 monthly. And we have all of that data. We can train our random forest model, and then we can make a prediction about who is going to non-respond in the wave of August 2019. Now, these propensity models, they output for each participant whose data you input into it, it will output a probability that they will non-respond in the next wave. And so we could say, for example, we've got a budget to intervene with 10% of our participants. So let's intervene with the 10% most at risk according to our model. What happens? So these are confusion matrices, and for those of you who are unfamiliar with these, I will talk through them. Top left, we've got a number. It says 4,625. These are people who we guessed who would respond in the next wave, and they did respond in the next wave. So 4,625 people we were right about. Bottom right, we have a number that says 241. What that means is our model and us choosing to target the 10% most at risk people means that we would have targeted 241 people with incentives, and those are the people who did non-respond. So those are the successful cases, the ones where we guessed they wouldn't respond in the next wave, and they would not have unless we, jump in and do something, say, for example. Next to that, we've got a number 206. These are the people who we guessed would respond, but then they didn't. Those are our false negatives. These are the people that we missed out on, and ideally our model would have caught them. And then our final number in this confusion matrix, 296, these are the people who we said we think they're going to non-respond in the next wave. They're at risk, but actually they would have responded whether we had done nothing or not. So if we had targeted them with interventions, that would have been that would have been a waste of resources. Now, if these numbers don't look very good, we're missing a lot of people. We're distributing a lot of incentives that went to people that it didn't need to be targeted at. Well, maybe that's because 10% is too restrictive. Let's relax things to targeting the top 20%. You can see now, bottom left in that center matrix, 109, we now only missed 109 people. So out of the 440 odd people who non-responded in the wave, we caught almost 3/4 of them, and we only missed about 1/4 of them. However, for every one person that we successfully identified as an at-risk person and then potentially intervened with them, there were roughly about 2 people, adding up to 736, roughly 2 people who we targeted when arguably we didn't need to. And this is what a model that has about 0.8 OROC, area under receiver operated curve, that we say is compared to other models in the literature is quite good. This is what that looks like. And so the take home here is that predictive performance is not 100%. These models don't have 100% predictive accuracy, but they have a certain level of predictive accuracy. So the question is, what can we do with performance like this? So bringing it back now to the temporal dimension, and this model that you're seeing here uses the rolling average response rate over the past 3 waves. And that was a technique for accounting for time that we arrived upon through trial and error. Okay, why should we care about the temporal dimension? Well, what we have here are two models. The random forest, which is something that's been shown to be a very effective model, and a long short-term memory, LSTM, which is kind of recurrent neural network. Both models have access to the same data, but the long short-term memory model can receive a time series of data and can exploit patterns that it detects in the time series. Whereas the random forest can only make a guess on the most recent piece of information that it has. And that is why you can see such a major difference between their two performances, with the exception of the coronavirus pandemic, which happened, shortly after the start of 2020 there for these panelists. And so you can see that this fairly large difference made by simply taking into account temporal dependencies as opposed to ignoring temporal dependencies. Okay, but this is a random forest that isn't accounting for temporal dependencies. What if we let our random forest use the rolling average non-response rate for the past 3 waves, which was something we found to be very effective in the Geesis panel? Then you find that the recurrent neural network and the random forest that is using rolling average non-response rates, actually they start to perform pretty much the same. An absolutely tiny difference in area under receiver operator curve scores. Basically nothing. They're basically performing about as well as each other. And what does this tell us? It tells us that the recurrent neural network, the long short-term memory model, and sitting next to that is GRU, gated recurrent unit. That's another kind of RNN that didn't do quite as well. But the LSTM is learning from the data that the rolling average over the past 3 waves is a good way to account for temporal dependency, and it's doing that automatically. The long short-term memory did not need to be told that rolling average over the past 3 waves was a good way to get high predictive accuracy. But with the random forest model, that had to be worked out through trial and error. And this is just to say that these recurrent neural networks can fit to temporal dependencies automatically. So what we want to say to you, practitioners of panel surveys and people who might be interested in developing your own propensity models, the time dimension matters. And it is good to experiment with lots of different approaches to handling temporal dependencies. And the recurrent neural network may be a good way of working out whether your particular model accounts for it as well as possible. If you fit a particular model and then you try a recurrent neural network and the recurrent neural network does better, this is an indication that you probably need to account for temporal dependencies in a better way. And you can either go ahead and use a recurrent neural network, or you can work out different ways of tuning, of managing your model to try and do that differently. So that is a close on our discussion of recurrent neural networks. And we are going to move on now to talk about some of the other areas that propensity modeling could move forwards in. So these are some of the areas that we want to push propensity modeling forward in. So firstly, we want to know whether this approach that we've outlined is robust. What's this approach that we've talked about so far? Well, it's basically using non-response history and demographic data as predictors, putting them in some machine learning models, and then seeing how well those machine learning models do. And lo and behold, you get area under receiver operator curve 0.8 and above. And that means that you can make predictions about as well as that applied example that we talked about earlier. And so far, we have just done this on one panel survey, which is called the Geesis panel. But does this same approach keep working again and again in lots of different contexts? Or are there certain kinds of panels that this approach just doesn't work in? Secondly, interpretability. So many of you may have heard the expression that machine learning models are a black box, meaning we don't understand how they're making these predictions. So we want to open up the black box a little bit and understand how the models are working, how these models are making those predictions, so that we can hopefully get to a point where we can explain a bit better why a particular person is given a particular propensity score. And then finally, if you are predicting non-response, that's all well and good, but presumably we want to do something about non-response and try to elicit at-risk participants to stay in our panel. So let's get going for point number one. Is this process robust? Does it keep working across lots of different panels? So to test that, we got together 5 different panel surveys. They are all German. That was easiest for us to manage over here in Germany. So we know that is one restriction, but otherwise there is a fair bit of variation between these different panel surveys, these 5 different panel surveys: SOAP, German Internet Panel, GESIS, Mannheim Corona Study, and the Frida Panel. What are some of the variations? Well, they vary widely in how frequently the waves come. So Mannheim Corona Study is was a weekly for 16 weeks panel study, whereas SOAP and Frida are annual, and German Internet Panel and the GESIS panel are coming every few months. They vary as to whether they're surveying individuals or households. They vary in what are the topics that they're asking, and they vary in the modes that they offer. So the question is this basic approach, non-response history plus demographics into a machine learning model, does it work on all of these different kinds of panels, or are there some kinds of panels that it is less effective in? And the answer, I should say that just quickly how we did this. Okay, so we have our 5 panels. We're developing our predictors, and we have done our best to develop an equivalent data set across the 5 panels. They all vary slightly in how they code what a non-response is, how they ask demographic questions like how large is your household. So we did our best to take into account these variations. And then having done that, now we have for all 5 panels a data set that we could throw into our common set of models, and then we can check how well they did. So how good was this general approach in all 5 panels? And the answer is pretty consistently good. So the worst performing panel in the long run would probably be the SOAP panel up the top there. And that's just to say that we get area under receiver operator curves of 0.8. But other panels, GIP and Mannheim Corona Study, we're seeing scores up above, or approaching rather, 0.9. But there's a bit of a pattern emerging here, and that is that all of these panels, after 3 or 4 waves, they seem to approach a long-term average level of predictive performance. But in those first few waves, usually in all of these panels except for SOAP, they're generally performing, most of these models are performing a bit worse, right? And that makes a bit of sense. Those of you who know some things about machine learning might know that the more data that you have, usually the better your model might perform. So, maybe the model needs to accumulate more waves of panels to start making better predictions. Why did SOAP do so well in its early surveys? We haven't looked into that in too much detail, but if I were to make a guess, my guess would be that it is because non-response rates were very high. Attrition was really high in those early SOAP waves, and that way it becomes therefore very easy to guess who's going to non-respond because so many people are doing so. Okay, so we've got this basic approach and we've tested it across lots of different panel surveys, and we've seen that it is working pretty consistently well across lots of different contexts. Even if you're changing the wave frequency, the mode, et cetera, still working pretty effectively. Sorry, not what I intended to do just yet. Whoops, there we go. So if we have this approach that is working consistently well across lots of different contexts, this opens up this possibility in machine learning called pre-training. Pre-training is where you train a model off, say, for example, one panel survey, and then you can use that model to make predictions about panelists in a completely different survey. So let's step through an example. So let's step through an example without pre-training. So the way that we would normally have to do this without pre-training, and we're back to the Geesis panel again, and we're going to step through this. So we're not pre-training here. So wave number one of the Geesis panel, well, we can't predict it. We can't predict it because there's no data with which we can train a model. The soonest you can train a model in a new panel survey is to wait for the second wave at least to complete, because you need the first wave for your predictors, and then you need the second wave to complete so that you know who didn't respond in that second wave. So you've got at least one data set for the outcome variable, which is non-response in the next wave. You need that data so that you can train your very first machine learning model. But once you have waited for this, once you have completed wave 1 and 2, now you can make a prediction about who is going to non-respond in wave 3. And over in the Geesis panel, we can see that it's just random forest that does pretty well, shy of 0.8. But it's the only model that does that well. These other models here do not do as well as that. And that's and this is us without pre-training. So we have to wait for wave 1 and 2 to finish. Then we can make a prediction about wave 3. The performance generally isn't as good as the performance will get once the model has accumulated several waves of data. But let's just say that we had a model ready to go before day 1 of the Geesis panel. This is a simulated example as if we had trained a model on the German internet panel, which started a year earlier than the Geesis panel, and it accumulated 4 waves worth of data by the time the Geesis panel started. And so this is a model that we can just immediately throw people's information into and get some answers. So people are responding or not responding to wave number 1. We throw their data into the model. How good are the predictions about non-response in wave 2? The answer is pretty lousy. Like I said, the worst possible OROC score you can have is 0.5. And these are, 0.55 to 0.6. So pretty terrible. What's going on here? Well, we're going to see later that non-response history is extremely important. Non-response history is an extremely important predictor of future non-response behavior. And as of wave 1, there is no non-response history to exploit. But as of wave 2, now we know who didn't respond in wave 1 and who didn't respond in wave 2. We have this absolute bare minimum amount of non-response history to exploit. We can put that in our model, and the prediction quality immediately shoots up. And in fact, it slightly exceeds 0.8, which is better than what we would have gotten if we had stuck with only a model that was trained only on its own data. So this is a model that was trained on 4 waves worth of GIP, German Internet Panel data, and it outperformed a model that was trained on only 1 wave of Geesis data, even though this is making predictions about Geesis panelists. So this looks quite nice for pre-training. However, the choice of what panel you use as your pre-training data matters. So this is what would happen if we had done it with data from the SOAP panel, which started in 1986 or 87. I'm sorry, I don't remember which one. But started decades earlier than the Geesis panel did. And if we had trained our model on SOAP, We again wave 2 still would have been quite well predicted, but only about as well as if we had not used pre-training. What are some of the things that we're seeing that cause one panel to be a better choice for your pre-training data than others? Well, two things. One, obviously, if they're closer together in design, so the wave frequency, the modes, etc. If they're closer together in that sense, that's going to improve its quality as a pre-training option. And then the other thing is actually how close is your data together in time. So data from the GIP came from 2012, making predictions about people in 2013. This is data from 1980s, predicting people from 2013. So of course, it didn't do as well. And then the final consideration for you all about pre-training, this is just about sheer predictive accuracy, but there are other advantages to pre-training, namely that if you have a pre-trained model, you can make predictions about people as soon as you have their responses. So if you have a field period of 2-3 months and you're trickling in responses, as soon as a response comes in, you can put that information into your predictive model and get a prediction out. If you had to wait until that data collection is completed before you can put that into your model to train on it, then obviously you must wait longer. So that is another consideration. And as we can see, extra time available to you to make an intervention, might help you do your response to these predictions better. Okay, so we just stepped through an example where we were targeting the geezers panel, but how well did this hold up? So what we have here is the every valid pairing of any two of our 5 panel surveys in which one of them came before the other. So Frida is the most recent. It started in 2021. So we can pre-train models on all of the other panels and then apply them to Frida. SOAP was the earliest one, and therefore there is no panel that we have that precedes SOAP. So we can't do pre-training on SOAP. So we can't do pre-training and then target SOAP, I should say. How well did they all do in that second wave, given that the first wave is never any good because there is no non-response history to use, but from the second wave onwards, we start to see better results. How well did everything do from the second wave onwards? And you can see some area under receiver operator curve scores ranging about 0.6 to about 0.88. So pretty good. And we have the baseline here, which is what if we had just used the panel's own data, and you can see some fairly substantial gains in performance, especially with regard to Frida. So if Frida had been trying to predict non-response in its third wave using only its own data, that would not have done very well. But with the benefit of pre-training models, we start to see some perfectly good predictive accuracy when it's applied that way. So that was about pre-training and its possibilities. We're in progress with a paper about that. We're excited to talk about it, excited about bearing out what we might be able to do with that technique.
Jack, we have a couple of questions, and I wonder before you switch, if we can maybe think about those, just because I think they apply to the previous part. And so the first one is, did you use all those models to train the data to get your results, or did you just use them to compare and agree to proceed with only one model to finalize your modeling?
Great question. So there's 2 parts to that. So those of you who are familiar with machine learning might know about something called hypertuning. And what that means is that each of these models here, there are various parameters that you can tweak about them. And so in any predictive paper, you want to know what was the guess that you could have made with the best set of parameters that you could have found at the time, as opposed to doing some kind of a 2020 hindsight analysis, whereby, you know, we say how well our models would have performed if we had have retrospectively picked the best one. That's one part of it, and the other part of it is I'm hearing, you know, did we select a particular best model? So in the paper, both the paper on recurrent neural networks and the paper about these models for pre-trainers, we did every kind of model, and we did every kind of set of tunings for those models, set of parameterizations for those models, and then we report all of those results retrospectively. And then in the paper, we do the best job that we can of showing what we could have gotten had we been making predictions at the time. And in this particular instance, what's happening at each time step is that we are determining the best model settings as of that given point in time, and then using that to make predictions and then presenting those predictions. So we are not using the benefit of hindsight when we are presenting how well the models did in terms of how we parameterized them, but we are showing you which one we are showing you all of these different models, these 4 ones: penalized, unpenalized, logistic regression, random forest gradient classifier. We're showing all of those at once. So say, for example, you know, over here in SOAP, gradient booster did the best in the first wave, but it wasn't the best in the second wave. Arguably, you wouldn't have known that if that was happening at the time. So that's just something to keep in mind when reading this. But I think we show that you know, if you were to take a look over several waves on average, you see that it's generally random forest that does the best, although all of them tend to do pretty much the same. So that's why we're not too concerned about this idea of the 2020 hindsight in that regard, because apart from a few important exceptions, they're generally performing about the same level. I hope that answers your question. Let us know if it doesn't, and we can move on to the next one, Mr. Harrison.
Okay, great. There's also a question. Could you kindly mention some of the considerations you made to take care of the variations and in the previous slides?
Sure thing. I apologize, but I'm not exactly sure I understand the to account for the variations in the way that we handle different data sources. Do I have the right interpretation?
And this is from Matilda Owino. If you could maybe toss in chat any clarification if I didn't get that right.
Okay, perfect. Thanks, Matilda. Sure. So, sure. So across 5 different panels, they all handle their data a little bit differently. You've got examples like household size. In the SOAP survey, you can put basically any number of people in as your household size, but in the GESIS panel, it's a multiple choice, and the largest option that you can choose is 5 or more. So we have to flatten 5 or more down to 5. Whereas for SOAP, it's, you know, it can be any number. Another one is that they all ask for monthly income, luckily enough, but some of them only allow people to enter multiple choices, and others allow you to input any number, leading to data quality issues like, you know, some people putting what we guess is something like they put their annual income into a monthly income thing. So if you take a look at the distribution of the same variable, but across different panels, you know, you can see that some panels have wild outliers or skewed distributions, and others don't have such things, and it's usually down to just little things like that. Another issue is that some of them actually record the reason for why something is a non-response, like whether it was a partial but unusable response, and others just binary code. You know, did we get a response? Yes, no. So there's some variations in that, and so we tried our best to keep to certain WAPOR definitions of what non-response is where we could, but otherwise some of the panels just you know, would just tell you whether someone non-responded as a binary yes/no variable, so we just have to use that. So those are that was the kind of adventures that we had in the data wrangling for across 5 different panels, trying to get something equivalent across all 5.
Thank you so much for those clarifications and elaborations. Thanks.
Okie dokie. Well, if we're okay to, we can move on, and I'll try, and we'll be moving a little more quickly now. So our next one is about trying to open up the black box of these machine learning models, trying to understand what is happening inside of the models. To try and see if we can explain, you know, why a certain person is predicted the way that they are. Now, we're not at the point where we are fully explaining predictions, but we can talk about what are the models doing? What are the models doing? So what we have here, this great big wall of numbers here for you, is what's called the feature importance. Feature importance is if I were to withhold this data from the model, how much worse would its predictions get? And that's an indicator that the model really relies on that data to make good predictions. And the takeaway here is that non-response history, non-response prior behavior, is really the most important thing when you're trying to predict future non-response behavior. Because the most important variables across all of the different models is historic non-response or non-response in the current wave, all of them except Frida, although we're arguing that we can sort of ignore Frida because Frida's predictive power was 0.6. It essentially failed as a model, and therefore we shouldn't care too much what its feature importances are. Also, Frida was only trained on some early waves, so there wasn't really any non-response history to use, explaining both why it doesn't rate it as very important and why it didn't do very well. But for the models that were successful, non-response history, very important, both the historic average and non-response in the current wave, given that I'm trying to predict non-response in the next wave. But that isn't all you need to make great predictions. The demographic features also help as well, and the most consistently helpful one is age. Other factors do help a lot, but they tend to vary between surveys. So which demographic feature is helpful in which panel study, there is some variation there, not enough that our generalizability and our pre-training completely fails to work, but enough to make us think, well, okay, there might be some interesting differences between panel populations as to what is actually sort of driving the non-response behavior. For example, this is something that we might be interested in thinking about. Well, marital status, maybe that affects household surveys differently to individual surveys, just for operational reasons, like there's more likely to be someone at the house, for example. These are just some conjectures, but the point is that it's non-response history and it's demographic data that is driving these non-response predictions. Primarily non-response history, but demographics help significantly improve predictions as well. So finally, and probably the most substantially, is what do we do with participants once we have predicted that they are at risk? And for this, I am going to hand over to Christoph.
Great, perfect. Yes, so for this last part, we will be looking at very recent research. So next slide. Where we are we conducted an experiment again in our kind of cases panel. For now, the experiment was done in a kind of way where we randomly allocated different treatments, but later on we will try to, well, kind of bring together those different treatments and interventions with our kind of predictions, and we'll do this step by step. But firstly, those different interventions are listed here. So we have 3 of them. So the first one is a bit of an unusual or innovative intervention where the respective participant were seeing or were given a version of the questionnaire that focused on their self-reported favorite topic. So we asked about their favorite topic in the previous wave of the cases panel, and then in this experiment, that random fraction here of the participant again saw their favorite topic, or that they reported to be their favorite topic. That was sort of one condition. The other condition is a classic. So that was a higher cash incentive than the baseline incentive that we used typically in the cases panel. And then the other treatment was a shorter version of the survey. So just try to reduce the burden with that treatment. And then clearly there's a control group. In addition to those interventions, also we clearly make use of prediction models again. So we kind of bring in all of those features and experiences, knowledges that we've talked about in the previous slides. And then we'll bring this to the table here to eventually also try to understand whether ML-based targeting of those interventions would make a difference. So we'll have 2 questions here. First one is, are interventions more or less effective for predicted high-risk participants? Because it's important as a prerequisite for an effective prediction-based adaptive design to understand whether our treatments actually also work for those folks that we predict to be at a high risk of non-response. And then clearly the central question is, how effective actually would a prediction-based adaptive design be? As I mentioned, this is very early, and we're still working on this part here. Next slide. Right, so for the first question, are interventions more or less effective for different groups of participants based on our predictions? Quick reminder here, so our predictions are sort of on the level of propensities or kind of predicted probabilities. We have a range from low predicted response propensities to high predicted response propensities for any participant. We will be focusing on different groups based on those predictions. So one group will be the high-risk group, looking at those 15% within the lowest propensity to respond. Then we have another group, which is the moderate risk group, that has still kind of a certain risk of non-response, but not the highest risk, but kind of the 15% above the mean risk. And the idea here is that those people might be more susceptible to interventions compared to the very high risk group. Right, next slide. So we use now those different groups to firstly just compare descriptively the non-response rate in the post-experiment wave. And there are 2 things to note here. The first thing is that for the whole sample, but also for moderate risk and high risk scenarios, and we see that compared to the control group, 2 interventions worked, which is the interesting survey and the cash incentive, which bring down the non-response rate to some extent. You see that the short survey was not a successful intervention in our case. The other thing to note is that for those that are being predicted to be at high and moderate risk to drop out, and they in fact also have then an actual higher risk or non-response rate in the post-experimental wave. So this is another way of evaluating that our prediction models actually do sort of a good job. Right, next slide. And the other takeaway is that we do see that the successful interventions, so the interesting questionnaire and the catch intervention is or are effective interventions across the board. So they are not just overall effective or reduce non-response risks, but they also do this for those that are predicted as being at a moderate risk and a high risk of non-response, which is an important takeaway because this is clearly needed then for making successful interventions based on our predictions. And this then is leading us to that very last part where we now try to combine all of this. And this is what Jack will be talking about.
Thanks, Christoph. So the final piece in our presentation here today is to bring it full circle. So we have presented these propensity models that estimate who is going to non-respond. But what we want to know is, well, what if we use the propensity models to try and target people with these different kinds of treatments to try to keep them in the panel? What would actually happen to the panel's overall non-response rate? And to do that, we're going to conduct a kind of simulation, but a simulation in which we try to keep assumptions to a minimum, which is to say that we're going to try and use only data from actual cases in this field experiment. And how we're going to do that is a little complicated. So please bear with me. What we're going to do is we're going to, we have our panel as it was all of the people who participated in our field experiment. They were randomly separated into the 4 groups, 1 control, 3 treatments. We're going to take that control group and we're going to randomly split it in half. We're going to randomly split it in half. What we're going to do is we're going to take the first randomly split off half, and we're going to use that as our, what if we had done no adaptive design whatsoever? No adaptive design done here. This is just what the non-response rate, for example, was in the whole panel, because it's the control group and it's randomly split off. So the non-response rate of that group C1 there should be roughly the same as the whole panel. It's our did nothing scenario. But the other half, C2, what we're going to do is we are going to take the highest, say, for example, we could take the high risk people, 10%, 15%, 35%, whatever, K% high risk people from this half of the control group, take them out and replace them with the high risk people from a given treatment group. And what this is simulating is, what if we had a budget to apply that treatment to 15% of the highest risk participants in the survey? So, for example, but what about if we're not targeting the high risk people, we're targeting the moderate risk people? What if we're using this treatment or that treatment? So all of these different scenarios we can repeat and repeat and repeat and simulate. And then there is a third piece to this, which is a particular baseline. So I've just said that we're going to compare a scenario in which we did an adaptive design to a scenario in which we did no adaptive design. But here's the thing, we're giving out treatments to people. We're giving out treatments to people. So we expect those treatments to have an effect. The question is, did targeting them with a machine learning-based propensity model actually help, or was it just the fact that we were giving out incentives? So we're going to introduce this this baseline here, which is this randomized allocation scenario where we took 15%, say, for example, of the participants, and we just randomly distributed out the given treatment. So that's to help us gauge whether it's the treatment that's making the difference or whether it's the targeting with the propensity model that's making the difference. So what was the results? So this is a somewhat complex figure, so I'm going to talk through it piece by piece. So we have these three subplots, and they are the different treatments. We have got these boxes, and these boxes are the distribution of outcomes across repeated simulations. We're repeating these simulations to account for the different random splits of the control group that we could make when we're creating our with adaptive design scenario and our without adaptive design scenario. There's random splitting there. We want to account for the randomness, so we repeat the simulation many times, and we get a spread of outcomes. The colors are these different numbers of people that we could have targeted. We could have targeted the 15% most at risk, the 25% most at risk, the 35% most at risk. That's the color channel. And then we have this zero line. That is because the y-axis here is how much did non-response rate improve? And what we mean by that is that a higher value on the y-axis means that non-response rate got lower as a result of our intervention. As a result of our use of adaptive design, we lowered the non-response rate by a certain percentage as described on the y-axis. And so the zero line is important because zero would mean no change. And if the value goes below the zero line, that means that our intervention actually made non-response worse. But the higher the value is above the zero line, the more effective our adaptive design was in limiting, in reducing non-response. And the values in the y-axis directly correspond to how much the absolute non-response rate changed. So for example, by targeting just 15% of participants with either the interesting version of the survey or the cash incentive, non-response rate for that wave came down on average in our simulated scenarios by 1 or 2%. So instead of a 7.5 non-response rate, we could have had a 5.5 non-response rate by simply distributing out an interesting version of the survey to just 15% of the high-risk participants. And that's actually got a really similar, if you like, outcome to targeting 35% of the participants with a quadrupled cash incentive. So that's just a finding that we're getting from this simulation, which is to give us an idea of how we could have brought together all these different kinds of treatments, all these different kinds of ways of using the propensity model to inform who we give the incentives to, and trying to compare whether it's the targeting mechanism via the propensity model that's making the difference, or whether it's just the fact that we're giving out incentives. And by comparing that with the random allocation, we can see that there is improvement made by the instances where we're using the models to target people. It's superior for interesting survey and for cash incentive to if we just randomly gave out the incentives, and so the propensity models are doing their job. So that's it for our simulation study, showing us what could be possible with these interventions. I believe I'll hand it over to Christoph now to wrap up.
Right. Yeah, exactly. Trying to summarize, so we had a lot of results, many things discussed. So I think one important takeaway is that we've seen across many previous studies, but also in our own work, that a non-response prediction is feasible, and we can receive very good performance scores there across different panel studies, different types of designs. There are many options for specific algorithms. There's a value in looking at tree-based models, I think in any case, and for specific cases, especially when we think about complex time series, or when we envision that the ordering of events matters, there's also value in considering RDNs. We presented this idea of pre-training prediction models, which I think is quite interesting, and specifically interesting for predicting non-response in newly established panel surveys, making use of data from other panels. And then lastly, this simulation wanted to essentially hint at the idea that actually pairing adaptive designs with ML can improve response rates in a cost-effective way. And as always, there is more research that needs to be done. We didn't talk about other outcomes. Clearly, non-response bias eventually is of interest. Long-term effects, so much more that can be done here. But with this, I think we stop for your questions, and we're very thankful for your attendance and look forward for any comments and suggestions. Thanks.
Well, Christoph and Jack, thank you so very much for this. We do have some questions. I have two from the chat, and we have one in the Q&A. Let me get first to the chat ones. And this is from Matilda Owino. Have you compared the paneled model data, or I saw that you compared the paneled model data and the unpaneled model data. Is that okay? As in, should all of them be tuned to the panel data to try comparing that and the like?
I can take that one, although sorry, I'm a little unsure as to what exactly we're referring to. Which comparison per se?
Matilda, if you could maybe toss in the chat something more specific there, I'm sure they'll be able to get at it. And maybe we can move on to another one from the chat. But Matilda, please just try to clarify a little bit the exact place where you were looking for. So you mentioned the RNN and LSTM in the previous slides. Have you tested to see the LTSM in the study of grouped panels? And besides, how many usable observations do you have for different panels? Thank you.
Great question. Thank you very much. Firstly, no, we excluded the RNN from this study. Not for any particular reason. It's just that the choice of model wasn't really what we were interested in here. It was just how generalizable are things and is pre-training sort of in concept possible. There's an infinitude of possible models to try, and we just had to draw the line somewhere. So we selected just the two most common models in the literature, which are logistic regressions and tree-based models. So that's why we excluded it, not for any more complicated reason than that. Number of cases, I'm sorry that I do not have a number off the top of my head. So one case is a participant at a wave. And I suspect that the number of participant at wave cases does not exceed 1 million, although it probably gets close.
Great. Thank you. So we have a question from Joel Ardiacha, and it's 3 questions in one. So in the models, historic non-response is summarized only as a rate. But because of its importance, would it be interesting to use more variables to account for different non-response patterns? 2, if they are panel members and there is known information from the participants, why not use attitudinal information about them instead of just non-response history and demographics? And 3, did you use the interaction between the probability of non-response and the heterogeneous effects of interventions? Why use the interventions to high-risk people who may not respond to treatments?
There we go, number 3 there. Did you use the interaction between the Very, very good question. Okay, yeah, thank you, Joel. Those are great questions. You are totally correct that just overall all-time historic non-response rate isn't necessarily the best way to account for time. And that was really the focus of our first paper with regard to the recurrent neural network is trying to look at all the different ways that you can account for the temporal dependencies, the order of events, the timing of events, whether events are in the distant past or the approximate past. And the conclusion of that paper is that the time dimension matters very much, and that there are several options out there. Because of this generalizability paper wasn't focused on that, we chose to exclude that and just do the one simplest thing possible, which was just take the all-time average non-response rate as opposed to doing this complex handling of temporal dependencies, which is an entire topic in itself. So just to keep things simple in this one particular paper is the reason that we did that. But it would be excellent, I think, to know whether certain approaches to temporal dependencies generalize between papers, especially because wave frequencies, potentially change things so much. So an excellent thing to look at in the future, but we excluded it from the current paper. If they are panel members and we know things about them, we could use attitudinal informations. We are. So we do so firstly, the reason that we stuck to just demographics and non-response is because it was always consistently available across all 5 of the panels. And so I know that we do collect that data in some, but not all of the panels. So we had to stick to data that was consistently available across all 5. And that's I would hazard the guess that for most panels, they ask you your basic details. And then also we just know non-response history as administrative data. But attitudes are in there for some of the papers, for some of the models, and we can throw them in there. I'll say this isn't reflected in any paper. This is just something that I noticed messing around with models, is that the attitudinal stuff doesn't significantly improve non-response predictions over what you've already got from non-response history, because non-response history is already such a good indicator that adding attitudinal information, at least in the very small number of things that I tried, didn't improve it in those cases. But that's not to rule out that it couldn't. Did you use interactions between the probability of non-response and the heterogeneous effects of interventions to use why use interventions of on high-risk people and not people who might be more likely to take it? The great question, and
Jack, I can also
go for it.
I can also jump in here since I think it's related to the part that I presented. So it's clearly super important. I think we're kind of also right now looking into sort of the heterogeneous treatment effects in more detail. I mean, there's a ton of work that can be done there. But sort of this broad idea is, I think, already reflected in this little comparison that I presented, where we said, okay, we want to look at focusing only on our predicted high-risk people, whether our interventions also would work or work there. And I think the preliminary results that we get hint at that. So it does seem to be the case that our interventions also sort of worked for our predicted high-risk folks. And the one intervention that did not work overall also did not work for the high risk folks.
Great. So Florian Grease has a question. Do you consider checking the newer SOEP waves? Because right now you might deal with both a difference to the other surveys, a time difference annually versus more frequently, and the era difference, 80s to 90s versus the 2010s. So two different things, the era and then the specific frequency.
I can go ahead and take that. Nice and simple answer. Thank you very much, Florian. Great idea. And so indeed we did do that. It's just that the result is in a visualization that's in the paper. We didn't include it in the presentation today, just because what we were trying to get across was that data from the more proximate past, is better. Indeed, data that is from the SOAP panel, but it is closer to 2013 when the predictions are being made does better than data from the 1980s. So sorry if we didn't quite get that across. Exactly that approach is sitting in our paper, and the answer is that yes, more proximate data does better. So I hope that answers your question.
And I think there's a clarification on Matilda Wino's a question just about the comparing the panel to the unpanel data. If you could go back to the slide you were just showing, I think she's wondering about this, sort of talking a little more about how you're comparing the panel and the unpanel data, just on the previous slide.
Is this the slide?
We're seeing the modeling setup. If you go to the data,
Okay.
yes.
Yeah, I think, yeah.
This one. Okay. And I'm sorry, I'm a little unsure about the question. These are all panels. These are all panel surveys. So I'm just a little unsure as to what unpanel data would refer to in there.
So thanks for that clarification. If there's anything else, please in the chat or in the share. And we are getting close to the end. I want to really thank both of you very much. Do we have any final questions or clarifications or thoughts? So we really want to thank both of you again very much from WAPOR. And for those of you who are attending, both WAPOR members and non-WAPOR members, we thank you very much for our attendance. For those who are non-WAPOR members, we have put in the chat a link that you can click on to join WAPOR, and that will give you access to all sorts of international experts and folks. And those of you who are APOR members, we're having a joint conference this year in St. Louis this coming May. So there'll be two sequential conferences. So I very much encourage those of you who are APOR members, especially to give WAPOR a try this year. For people who are new to WAPOR and not sure if you're going to if it's really for you, we have a Friends of WAPOR membership as well, where you can give it a shot at a try at a reduced membership fee or a reduced friend fee. But I would very much like to thank Christoph and Jack, and look forward to seeing you again at our next webinar. Thank you.
Thank you for having us.
Thank you very much,
Thanks.
everybody.